Welcome to Section 6, Lesson 10. Across the previous 9 lessons, we built every system solving skill. The rest of the algebra course depends on systems of equations, introduction with 3 solution categories, substitution method with the isolate and replace mechanics, elimination method with the equal and opposite coefficient construction, choosing the right method based on the system structure, special cases of no solution and infinitely many solutions. 3. Variable systems with sequential variable elimination. Word problems with the translate, then solve workflow, systems of inequalities with feasible regions and corner points, and linear programming with the corner point theorem and 4-step optimization procedure. Today is the marathon lesson where we apply all 9 skills back to back on a mixed sequence of challenges. Mixed practice is the most efficient learning move in all of mathematics because it forces you to first identify the type of problem and only then apply the relevant rules, which is exactly what tests, contests, and applied work demand. Section 6 closes with this marathon, and the next section opens with polynomials. First idea on the board. Mixed practice exposes the soft spots in your skill set in a way that single topic drills never can manage to do for you. When every problem in a homework set is a substitution problem, your reflexes carry you through without much thought. When the next problem might be substitution or elimination or a 3-variable system or a word problem or a system of inequalities or a linear program, you really have to first decide which toolkit applies and only then start the actual solving work. The decision step is exactly where weak students stumble and strong students breeze through with confidence. Today we exercise that decision step deliberately on a mixed sequence covering the full Section 6 scope from start to finish. The full Section 6 toolkit has 9 skills, and you should really be able to name them all from memory before starting the marathon. Systems of equations introduction with the 3 solution categories of 1 solution, no solution, and infinitely many solutions. Substitution method with the isolate and replace mechanics. Elimination method with the equal and opposite coefficient construction step. Choosing the right method by inspecting the system structure for already isolated variables, equal or opposite coefficients or fractions. Special cases of no solution producing a contradiction and infinitely many solutions producing a tautology, both detectable by the algebra collapse pattern. 3. Variable systems with sequential variable elimination across pairs of equations. Word problems with the translate, define, solve, check workflow at every problem. Systems of inequalities with feasible regions, half-plane intersections and corner points. Linear programming with the corner point theorem and the 4-step procedure. 9 skills, all interconnected, all needed continuously for the rest of the algebra course and into precalculus and calculus and applied optimization. Third idea, speed and pattern recognition on mixed system problems come only from doing reps, never from reading the rules in a textbook. The rules from Section 6 are short enough that 2 or 3 hours of careful reading actually covers all of the formal content very thoroughly. Just to get you really going on this, commit to working a similar mixed set on your own time over the rest of the chapter, and the Section 6 material will lock in as automatic background knowledge that the rest of the algebra course can build on without any conscious effort whatsoever. The fluency that lets you solve a mixed system problem in under a minute rather than 4 or 5 minutes comes from 60 or 80 practice problems spread across the next 3 weeks of homework practice. The marathon today is a starter set. The full Section 6 toolkit has 9 skills, and a marathon-style mixed practice session is the most efficient way to lock them in as fluent reflexes for the rest of your algebra career. The first move on every mixed problem is to identify which skills the problem requires. Only after that identification do you actually apply the relevant rules. Today, we make the identification step explicit so you can train it deliberately rather than absorb it by accident. Skills 1 through 3 are the foundations of two-variable system solving. Systems of equations introduction with the three solution categories: a unique intersection point, parallel lines with no solution, or coincident lines with infinitely many solutions. Substitution method with the isolate and replace mechanics, used when one variable is already alone on one side or has coefficient 1 or -1. Elimination method with the equal and opposite coefficient construction, used when no variable is isolated and especially when fractions appear in any coefficient. Skills 4 through 6 are the structural and special case layer. Choosing the right method by inspecting the system's structure. A substitution wins when one variable is isolated. Elimination wins for symmetric coefficients or fraction-free coefficients. Either method works for plain integer coefficient systems. Special cases of no solution producing the algebra, collapse contradiction like 0 equals 5, and infinitely many solutions producing the algebra, collapse tautology like 0 equals 0. 3 variable systems with sequential variable elimination. Combine equations pairwise to remove one variable, then solve the remaining two variable system, then back substitute for the third variable. Skills 7 through 9 are the application and optimization layer. Word problems with the translate, define, solve, check workflow. Define decision variables, translate every English sentence into one equation, solve the resulting algebraic system, check the answers in the original problem statement. Systems of inequalities with the half-plane intersection technique, graph each inequality as a half-plane bounded by a line, intersect all the half-planes to find the feasible region, identify the corner points where boundary lines meet. Linear programming with the corner point theorem. Any linear objective over a polygonal feasible region attains its optimum at one of the corner points, so the four-step procedure of graph, corners, evaluate, pick, reliably solves any LP. All 9 skills are mechanical once practiced and produce exact answers reliably for any well-posed problem. The marathon today exercises every one of them across 2 extended worked examples, and the next homework set should mix them again at higher density to lock in fluency before Section 7 on polynomials begins. Marathon Problem 1, word problem requiring system setup, method choice, solving, and checking. A theater sells adult tickets at $12 and child tickets at $8. On a Saturday show, the theater sold 140 tickets total and collected $1,360 in revenue. How many adult tickets and how many child tickets were sold? Step 1. Identify the problem type. 2 unknowns, 2 relationships in the story. Ask for both quantities. This is a 2-variable linear system word problem, skill 7 combined with skill 2 or 3. Step 2. Define decision variables. Let A equal the number of adult tickets sold and C equal the number of child tickets sold, both non-negative integers in this real-world context. Step 3. Translate the story into equations. Total tickets A plus C equals 140. Total revenue 12 A plus 8 C equals 1360. 2 equations, 2 unknowns, ready to solve. Test the method. The first equation has A alone with coefficient 1, so substitution is fast. A equals 140 minus C. Substitute into equation 12 times 140 minus C plus 8C equals 1360. Step 5. Distribute to 1680 minus 12C plus 8C equals 1360. Combine 1680 minus 4C equals 1360. Subtract negative 4C equals negative 320. Divide C equals 80. Back substitute A equals 140 minus 80 equals 60. Step 6. Check in the original story. 60 plus 80 equals 140 tickets total, correct. 12 times 60 plus 8 times 80 equals 720 plus 640 equals $1,360 revenue, correct. Both relationships verified. So the theater sold 60 adult tickets and 80 child tickets. Lesson 1 Word problems reduce mechanically to algebraic systems once the variables are defined and the relationships translated. Substitution is the natural method when a variable starts isolated. Marathon problem 2. 3-variable system requiring sequential elimination paired with structural method choice. Solve the system x plus y plus z equals 6, x minus y plus 2z equals 5, 2x plus y minus z equals 1. Step 1. Identify the problem type. 3 unknowns, 3 linear equations. Ask for all 3 values. This is a 3-variable system, skill 6 combined with skill 4. Step 2. Choose elimination as the method. No variable is isolated. Equal or opposite coefficient construction across pairs is the natural fit. Target eliminating y first because y has coefficients 1, -1, and 1 across the 3 equations. Step 3. Eliminate y from equations 1 and 2. Add equation 1 and equation 2 x plus 3z equals 11. Call this equation A. Step 4. Eliminate y from equations 2 and 3. Add equation 2 and equation 3 3x plus z equals 6. Call this equation B. Step 5. Solve the 2-variable system in x and z equations A and B. 2x plus 3z equals 11, 3x plus z equals 6. Solve B for z equals 6 minus 3x. Plus 3 to A, 2x plus 3 times 6 minus 3x equals 11, which simplifies to 2x plus 18 minus 9x equals 11. Then negative 7x equals negative 7, so x equals 1. Back, substitute z equals 6 minus 3 equals 3. Step 6. Back substitute into equation 1 for y. 1 plus y plus 3 equals 6, so y equals 2. Solution at x equals 1, y equals 2, z equals 3. So the 3-variable system has the unique solution 1, 2, 3. The big lesson from the marathon is that Section 6 skills compose. Word problems use system setup. 3-variable systems use repeated 2-variable elimination. Linear programming uses corner finding from systems of inequalities. The entire chapter is a single connected toolkit. Practice the identification step deliberately on every problem, and the section locks in as fluent algebra forever. 3 mistakes that catch every algebra student during marathon-style mixed practice. Each one is fixable with a small explicit habit applied on every problem from now on. First mistake, skipping the identification step and starting to solve before deciding which method or skill the problem actually requires. A student in a marathon set sees a system of equations and immediately starts applying substitution, then realizes halfway through that elimination would have been twice as fast, then has to backtrack and restart. The fix is to always pause for a few seconds at the top of each problem to identify the problem type and the natural method before writing any algebra. Identification is fast, it costs 5 seconds and saves often 2 or 3 minutes per problem. The discipline of always identifying first is the single biggest accelerator on mixed practice sets. Second mistake, picking a method that does not match the system structure. A student uses elimination on a system where one variable is already isolated and ends up rewriting equations and constructing equal or opposite coefficients when substitution would have given the answer in 2 lines. Or uses substitution on a system with fractions and creates fraction stacks that take 5 steps to clear. The fix is to internalize the structural rules from skill 4. Substitution wins on isolated variables and integer coefficient 1. Elimination wins on symmetric coefficients and especially fractions. Either method works on plain integer systems. Match method to structure on every problem. Third mistake, solving correctly but skipping the final check. A student arrives at a solution, writes it down, and moves to the next problem without plugging the values back into the original equations to verify. A small sign error or arithmetic slip in the middle of the solving process corrupts the final answer, but the check would catch it immediately. The fix is to always plug the solution back into every original equation before declaring the problem done. Checking takes 30 seconds, catches roughly 1 solving error in 5, and is a non-negotiable habit on every algebra problem from now on through the rest of your math career. The Section 6 skills cluster appears across engineering, operations research, economics, finance, and computer science continuously. 4 broad sectors below where every working professional applies these algebra-level techniques routinely. In engineering analysis, equilibrium equations in mechanics, circuit analysis with Kirchhoff's laws in electrical engineering, and force balance in structural engineering all reduce to linear systems with multiple unknowns. The substitution and elimination methods you practiced in Section 6 are exactly the techniques that engineers use by hand on small problems and that engineering software solves on large problems with thousands of unknowns. The mathematical machinery scales directly from the 2-variable and 3-variable systems in this section. In operations research, production scheduling, vehicle routing, workforce assignment, and resource allocation are all formulated as systems of linear constraints with linear objectives, exactly the linear programming structure from Lesson 9. Companies like Amazon, FedEx, UPS, Walmart, and Boeing run linear programming software continuously at industrial scale, with each LP solving in seconds despite containing millions of variables and constraints. The corner point theorem and the 4-step procedure you learned today are the conceptual foundation of all of this work. In economics and finance, supply and demand equilibrium reduces to a 2-equation linear system between buyers and sellers. Portfolio optimization with risk and return constraints reduces to a constrained optimization problem of the same shape as linear programming. Input-output analysis in macroeconomics, the Leontief model that won a Nobel Prize, is fundamentally a large linear system with hundreds of variables. Section 6 is the algebraic gateway to all of these economic models. In computer science, linear systems show up in computer graphics for projection and shading, in machine learning for least squares regression and neural network gradient descent, and in constraint solvers and SAT solvers for automated reasoning. Modern software systems running on phones and servers depend on solving linear systems millions of times per second, and the algebraic foundation is exactly the Section 6 material from this chapter. 3 things to take with you from this lesson today. Section 6 closes with this marathon, and the next section opens with polynomials, which are an entirely different kind of object that we treat with completely new techniques. First, identify the problem type and the natural method before writing any algebra. Identification is fast, costing only a few seconds, and it saves minutes of wasted work on long problems. The identification habit is the single biggest accelerator on any mixed practice set, on any test, and in any applied setting where the problems do not arrive labeled by topic. Train it deliberately on every problem from now on through the rest of the algebra course and beyond. Second, match the method to the system structure. Substitution wins when one variable is already isolated or has coefficient 1 or -1. Elimination wins on systems with symmetric coefficients or fractions. Either method works on plain integer coefficient systems. The structural rules from Skill 4 are the decision tree, and applying them mechanically on every problem prevents the wrong method mistake that cost students minutes of unnecessary algebra on otherwise easy problems. Third, always check the final answer back in the original equations before declaring the problem done. Checking takes 30 seconds, catches arithmetic and sign errors before they become wrong final answers, and is a non-negotiable habit through the rest of your math career. Section 6 is now complete in its entirety, 9 skills, all practiced, all interconnected, all locked in as fluent algebra ready for the rest of the course. Coming up next, the lesson called Introduction to Polynomials, which opens Section 7 by introducing polynomial expressions as the next major class of algebraic objects beyond linear ones, with a brand new structure built on degree, leading coefficient, and term arithmetic.